Hello ladies and gentlemen, today our focus is on magnetic force of moving charge. Now, it is continuation of left-hand rule number 3. We already learned a little bit of concept, Fm that is equal to ILB, which is a situation that we use not only for using rule number 3 for left hand for negative or right hand for positive, but also when we actually distinguish the force that is applied perpendicular to each other to electron carrying wire or external magnetic field. We are doing very similar situation, except our focus is, like the title says, moving charge. Either positively charged subatomic particle like proton, or it can be alpha particle in unit B, or negatively charged particle, which is electron in unit B. When it comes to unit 4, when we learn about atomic physics, we're going to deal with some situation where negatively charged ion and positively charged ion situation. Let's do a little bit of recalling of it. Let's say we have two pairs of wire that carrying a same current versus opposite current. When it comes to rule number 1, remember, thumbs up, thumbs down, these situations are the rule number 1. Your thumb represents where the electron goes, so in this left situation, it's into the page, and my forefinger that is curved counterclockwise. So I'm gonna just extend that drawing, and when it comes to the other one, same stuff. However, my focus should be in this middle area. What's happening in there? Do they attract to each other, or do they repel against each other? If I look at the midsection, let's focus on the bottom area. You may notice that the vector is aligned, which means in this situation, they attract each other. Like south on the left side, north on the right side, you can see that trend. When you look at opposite current carrying wire situation, into the page and curve, out of the page and curve, let's focus on these two areas again, then you can notice that I have going to the right, going to the left. In this situation, they repel each other because those two vectors are fighting against each other. These situation, I like to call any type of wire situation, is easy to deal with. You may not necessarily need to use rule number 3 for calculation. But what if proton, electron are the one, those sphere source charge, are the one that is experiencing any type of motion inside of an external magnetic field? What's going to happen? And that is today's portion. Before we're getting into formula, let's go with our theory section first. One thing that you need to understand, ladies and gentlemen, is when it comes to any type of charged particle that is going into external uniform magnetic field, it's going to undergo circular motion. And I'm going to explain to you why. So let's look at the scenario on the right side over here. I have magnetic field that is going into the page. On the other hand, electron, as you may see, is in fact shooted towards east or right, whatever you want to call it. When it comes to any type of charged particle and magnetic field, and when I say magnetic field, external magnetic field interaction, you have to use left-hand rule number 3 for your electron or negatively charged ion in future, or proton, alpha particle, any type of positively charged ion situation using the right hand. So in this case, you have to use left hand. Remember, 4 fingers represent external magnetic field. So 4 fingers are going into the page. And my thumb, ladies and gentlemen, should be aligned with the velocity or speed in this case, which you will know why I'm going to use a quantity only scalar situation later. But where this that direction of curve for the electron. So you may notice that my palm, which is going down situation, this is my force direction. Using my rule number 3, like what we learned last week, this is what's happening. And if I actually going into this external field, here's what's going to happen. My palm's going to push it down, push it down, push it down, push it down, push it down. So what's going to happen is force will face toward the center of the circle. And we learn about this in Physics 20, in Unit C, in fact, when you guys learn about circular motion. This is like centripetal acceleration and velocity make 90 degrees to each other. So here's my derivation of formula. First thing first, since a circular motion, Fc is equal to mb squared over r. Now, in circular motion, this Fc, centripetal force, it's kind of resembled to your net force, basically. If you have these two forces, ladies and gentlemen, your next goal is, what is the forces that existing in this system? Because net force is addition of every single force that is existing in this system. And right now we only have one, Fm. And this is the formula that you guys will use. Fm, that is equal to Q times V times V. Q times V times V. If I highlight only the few stuff in this situation, Q is magnitude of the charge. Let's not even talking about positive and negative, because positive we use right hand rule, negative we use left hand rule. By using those two specifically different rules, we know that we can differentiate the vector. So we're talking about just the quantity in this situation. V represents the speed. Why we are not using velocity is because as soon as we're getting into the magnetic field, this is circular motion. In circular motion, the velocity is 90 degrees always to the acceleration, which is centripetal acceleration, and because of that, V is uniform. It doesn't change. You don't accelerate in grade 12 situation in high school. And B is my magnitude of external magnetic field. Of course, when it comes to those, we need to use hand rule number 2. Sorry, hand rule number 3. So by combining this Fm situation, how this net force, which is Fc, will play is that should be equal to Q times V times V, which is what you just see up there. That's my derivative. In here, let's isolate for the perspective of speed. It can be radius, it can be magnetic field, depends on the situation. But let's do the isolation of V. Some people get struggle because this perpendicular sign throw people off the bridge, but consider that as exact equal quantity as V on the other side. So long story short, if I derive one of the quantity in here, which is variable, sorry, QB R over M. QBR over M. That's my speed that you can find. And of course, depends on diploma questions. It can be radius you need to find, it can be Q, it can be magnetic field that you need to set up the machine, something like that. This concept is basically used a lot in mass spectrometer. And that part, we're going to deal with that more when we approach to Unit D. This is ultimate technology that use, I have, for example, mercury sample from this river, and can you analyze? We basically change the machine setup and find out, oh yes, it actually had mercury, or no, it doesn't have mercury, in fact it has any other mineral, something like that. It uses it for quantitative analysis in real life. Let's do a quick example. Number one, if the diameter is 9.0 centimeter in this external field, then, there you go, that's better. Let me just read this question one more time. There you go. It's on the next page, folks. If the diameter is 9.0 centimeter, then I need to determine the direction of B and the speed, V, of this electron. First thing first, since we're talking about negatively charged negatively charged subatomic particle, I need to use left-hand rule, basically. Now, your next part is find out some of the clue. We have external magnetic field that is given. Now, know the fact that direction is not given. Is it into the page or is it out of the page? So we gotta find out. Let's use left-hand rule. What will be the situation? Let's talk about what if it's into the page. If I bring my forefinger into the page over here, you may notice that my palm is facing the west direction, which means the circle should have been drawn like this, which is not. The circle is actually going towards the east. So in fact, it's a little hard to describe. As you may notice, my forefinger is outside of the page, and then my palm is facing east. So, long story short, inside of this box over there, magnetic field must go out of the page. That's what you need to understand. That's the only case where my force will start bring everything towards the center, which is, apparently it's hard to see in here, but center of the circle probably located over here, and the force will go towards that center. And have that in your mind. One more thing. Although diameter is given, diameter is 0.090 meter, it's a good idea to have a little habit of making everything into meter by doing unit conversion. Always try to find radius. Because NV square R, which is FC formula, my centripetal force situation, you need to understand that this R is the one that we use, not the diameter. So get your calculator ready. Unfortunately, I don't have a calculator on this computer, the fancy version, so I'm going to use my Texas Instrument calculator. So 0.090 divided by 2 will give me 0.045 meter. So I have radius and I have magnetic field, which is 240 microtesla. Micro means 10 to the power of negative 6. So 240, 10 to the power of negative 6 Tesla. So you have those two. And basically, we are going to find out every single question that is involved with finding out the speed amount. First thing first, direction of B, we already checked it. It is out of the page. That's my answer for me. So B, let's think about it. My net force, in this case Fc, I have magnetic force, and that's about it. I don't have any type of gravitational force because you can see it as a left and right. Unless it's specified, like Millikan's oil drop, you need to understand that whatever the clue that is given, you need to list it. Don't go overboard. Even if you think about gravitational force, it's not a concept of your projectile motion in a parallel charged plate situation. Now, let's put some number in. This is technically MAC. In case if you don't know where the mv squared over r come out, mass times acceleration, except it's centripetal, QBB. Acceleration, you can find the formula n and then b squared over r. This is thus why the formula On a previous page, mv squared over r came out, and qvb. And now we can cancel one of the velocity, isolate for r. Then you will have r is equal to nv over qb. And we're punching the number in. Electron, mass of an electron, you can find it from your formula sheet. 9.11 10 to the power of negative 31 kilogram. Times by speed. Oops, ladies and gentlemen, I isolated wrong. It was asking about the speed, not the r, sorry. Then it's actually a little easier because we just did that. QB r over m. Whenever you do mistake, don't get panicked. Then punch these numbers in. And just the amount, please. 1.60 10 to the power of negative 19, 240 times 10 to the power of negative 6, times by r, which is 0.045 meter, divided with mass 9.11 10 to the power of negative 31 kilogram. So everything should make this into meter per second. It will be fast. If I round it up to significant digit, which is two significant digit, it should be 1.9 10 to the power of 1, 2, 3, 4, 5, 6 meter per second. Know the fact that when it comes to your velocity and speed, you cannot exceed speed of light, which you're going to learn it in Unit C. Speed of light is 3.00 10 to the power of 8. If you have something bigger than that for your speed, you're going to shout again. You may put some exponent in a wrong place. Have that in your mind. That is my lesson for today. Please solve every question in homework section, both A and B portion. Thank you very much.